Alright guys, this is topic 51, the derivative of an exponential function and the derivative of Euler's number. Okay, so I'm going to skip through some of this stuff. You can write this out if you want. All that says right here, if you notice, as this number is getting closer and closer to 0, which is what this limit is, if you have any equation that looks like that, then as this goes to 0, as that gets smaller and smaller, then that's going to be equal to the natural log of a. Okay, so now where I'm going to start, and again, this is optional if you want to write the next few things that I write here, right? So you don't have to write them. I'm just going to show you where some of these formulas are coming from. So if we have the limit, all right, so if I take the derivative of this right here, however, I don't know how to take the derivative of that. So what I'm going to do is I'm going to use the formal definition of a derivative, which is what I wrote right here, and I'm going to use that on this, all right? So remember, f of x plus h is actually a to the power of x plus h. Right, f of x is ax, and h, well, that's just going to stay h. And I'm going to put that as a goes to 0. All right, by the rules of exponents, that is from lesson 50, you know that this right here would be the same thing as having ax times a to the h minus a to the x. Okay, all of this is over h. So what's going to happen in the next step, remember, right, if I added this exponents, that must have meant that eventually, or sometimes, I can actually rewrite this as a to the x times a to the h. Okay? So now, as I look at this, I'm going to factor out an a to the x here. So, continuing on with this, this would be the same thing as a to the x. Alright? I'm going to write this, and I'm actually going to move that limit out here now. So therefore what I have left here is a to the h minus 1 over h. Okay, but remember, alright, so I moved this a to the x from, normally was right here, I moved it out over here, which I can. Alright, so now what you have left, and notice that I'm able to do that because this doesn't have an h anymore. I can move it out anywhere I want to. Okay. So now what ends up happening is that this part right here, this part, is exactly as this right here. So all of this becomes the natural log of a. Alright, so f prime of x will be equal to a to the x, and this right here became the natural log of a, right there. So we do all that just to tell you that if you're taking the derivative, and remember, this means you're taking the derivative with respect to x of some exponential function, right? Meaning that the variable is in the power. Right? So if you're taking the derivative of an exponential function, the derivative of that will be the natural log of the base times that exponential function. Right? So the derivative of a to the x is equal to natural log of a times a to the x. Okay, so I'm going to write an example here that also proves this next one coming up, because this one and this one are related. They're basically, this one came from here, but I'm going to show you how. Alright, so let's say that I have some example, and I'm trying to look for the derivative of 2 to the x power. Alright, so the derivative of 2 to the x power, using this formula, the derivative of that would be 2 to the x times the natural log. Every time I write natural log, I want to write an h. It's programmed into my brain. Alright, so 2 to the x times the natural log of 2. Okay, so that's pretty much for that example. That's it. Alright, another example that I can show you is if f of x is equal to e to the x, then the derivative, using the same exact formula, that would give us e to the x times the natural log of e. But if you remember from pre-cal and algebra 2, the natural log and e, Euler's number, are inverses of one another. So this one is actually goes to 1. Alright, so because they're inverses of each other, they kind of cancel each other out. So the answer to this, the derivative of e to the x, is just e to the x. And that's it. Okay, so those are the two formulas that you have right here, right? So the derivative of e to the x is just e to the x. And then finally, if you're taking the derivative of e, but this power appears as a function, all right, so imagine that u is some kind of function, differentiable function of x, then the derivative of that would just be e to the u times the derivative of that power right there. All right, so let's go through some examples on the back just to kind of show you what's going to happen. All right, so on this one right here, example 1, all right, the derivative of this is going to be equal to 2. Remember, this is just a constant. The 2 is just a constant, all right? So I'm just going to keep dragging that constant. You could potentially do product rule here if you wanted to, but because 2 is a constant, you really don't have to, right? So this would be 2 times the derivative of 3 to the x. Right, the derivative of 3 to the x by those formulas that we just finished working on, and this is right here. All right, that's that formula that I'm using. This would be 3 to the x times the times the natural log of 3 plus the derivative of 5 e to the x would be 5 times the derivative of e to the x, if you go back and look at that formula, is just e to the x. So that didn't change at all. All right, so one more time, take a look at it. The derivative of e to the x is just e to the x, okay? So that's it for that. I guess just to, let's see if I want to simplify this. You don't have to. Like this step is just, I don't even know why I'm doing this step, but you could potentially, if you see it like this, it could also be rewritten like this with the 3 to the x here plus 5 to e to the x. But I mean, either one I'll take. I'm just showing you two different ways I could potentially write this. Okay. Now in example 2, and this is the last formula was right here. If the power is some differentiable function, okay, then I'm going to use this right here. All right, so I'm actually going to write the formula here just to make sure we are all on the same page here. So if this is the derivative of e to the x, e to the u, derivative of that would be e to the u times du dx. Okay? So that's what the formula. So right here I just rewrote the formula so you don't have to keep flipping back and forth. So now the derivative of this therefore would be, where u, by the way, u is the tangent of x, and du dx would be the derivative of tangent, which is secant square. Alright, so this is where I'm going to get this stuff from. So I'm just going to replace that. Alright, so we have e times the tangent of x, e to the power of tangent of x times the secant square of x. That's it. There's nothing else to do about that. Alright, so this is it. Alright, that's that. Let's go to example 3. Now notice in example 3 we have a function x times the function e to the power of 2x. So in this one, because you have a function times a function, then you're going to need to do the product rule. Alright, so we're going to do the product rule in this one. So the derivative of this will be, let's see, dy dx, and that's equal to the first, which is x, times the derivative of e to the 2x. The derivative of e to the 2x would be just kind of like this one, would be e to the 2x times the derivative of 2x, which is just 2. Okay, plus the second, which is e to the 2x, times the derivative of the first. The derivative of x is just 1. Alright, so now just to simplify this, this would be 2x, e to the 2x, plus e to the 2x. Alright, and potentially if you see something like this in a multiple choice, I could potentially factor out the e to the 2x. You don't necessarily have to do that. Alright, but if it's a multiple choice question, this could be one of the answers. Alright, so that's that. Alright, in example 4, if you look at it, now we have a function divided by a function. So that means that we're going to have to do the quotient rule. Alright, so we're going to do the quotient rule. So we have low d high, the derivative of that one right there. Remember, 3 to the x is a differentiable function, right? So the derivative of e to the 3x would be e to the 3x times the derivative of 3x, which is 3. Minus, so low d high minus high d low. Alright, so now I need the derivative of this right here. The derivative of 1 is 0. The derivative of e to the x is just e to the x. So that's it for that. Over the bottom square, over low square. Okay? So low d high minus high d low over low square. Okay. So now just to simplify this at this point, I'm just going to simplify. So notice that this right here, by the way, is 3 e to the 3x if you just put that 3 in front. Alright, so this right here you would have, if I distribute this among those two, I'd have 3e to the 3x plus 3e to the 4x. Now, I can see some of you might be looking like, where did he get that? Remember, this is e to the 3x, and if I multiply e to the 3x times e to the x, when I multiply two exponential functions, I add the powers. So x plus 3x is 4x. That's where I got that from. All right? And then now on this one, e to the 3x times e to the 3x times e to the x is equal to e to the 4x. Also, same idea. If I multiply those two, I'm going to add the exponents. All right, all of this over 1 plus e to the x, all of that square. All right, and potentially, let's see what else we can do from here. Okay, yeah. So notice that you have like terms here. You have 3e to the 3x minus e to the 4x. Plus 3e to the 4x. So these two right here, excuse me, might have said that wrong the first time. These two are like terms. So I'm going to add those two. So this right here would be 3e to the 3x plus 2e to the 4x over 1 plus e to the x to the power 2. All right. Now, last but not least, oh man, this one sucks. All right. Notice that right here, I'm going to have implicit differentiation. All right. I could try to solve for y, but that's going to be kind of difficult considering that this y up here is a power and this one's not. So I'm going to do implicit differentiation. All right. So I hope you remember that. So the first thing I have to do is I'm going to take the derivative of this. I'm just concentrating on the derivative of e to the power of xy. All right. So the derivative of that would be e to the power of xy times, remember, this is from the formula that I just finished doing. This is this formula right here. E to the u du dx. All right, so this looks like a minus. I'm sorry. That's just a scribble. I'm sorry. So the derivative of x times y, notice that you have a product rule. All right, so then I would have x times the derivative of y. The derivative of y would just be dy dx. All right, or 1 dy dx. Plus the derivative of x, which is 1, times y. All right, so this right here came from taking the product rule of xy. All right, so this is where this came from. Okay, I'm just doing this so you'll be able to tell that that's where this came from. All right, this right here came from taking the derivative of x times y. All right, so that's that part. Now the derivative of x squared, that's just going to be simply 2x, and the derivative of y squared is going to be 2y dy dx. Hopefully you still remember all this. It's equal to the derivative of a constant is 0. All right, so if you remember from the past here, what we're going to do first is we're going to try to get the dy dx's by themselves. Okay, we're going to try to gather all the dy dx's on one side. So before I do that, I'm going to go ahead and distribute this, all right, because I can't think of any other way to do this, to be honest. So we have e to the power of xy times x dy dx plus y e to the power of xy. What else? Plus 2x minus 2y dy dx. And that is equal to 0. Alright, so notice that now what I'm going to try to do is I'm going to try to subtract all the non dy dx terms. So I'm going to try to keep this one here. I'm going to try to keep this one here. I'm going to move both that one and that one to the other side, okay? So now, what I'm going to do here, I'm going to go step by step so not to lose you. I'm going to write this over here like this now. But this is the same thing as this. I'm going to subtract that and that from both sides. So I get negative 2x minus y e to the power of xy. Alright, now I'm going to factor out a dy dx here. So I have dy dx that's what I got so far. And then now finally, I'm going to divide both sides by x e to the xy minus 2y. And that cancels that. And basically what I'm going to get right here will be the answer. Okay, so again, all this was just a bunch of examples. If you have any questions, make sure to ask me when I see you. Alright, if you're watching this, the test will be after I cover lesson 42. Sorry, excuse me, lesson 52. So, we'll see you next time.